Welcome to our first of 3 videos on working with measurement numbers. In this first video, we're just going to look at how to determine the precision and the accuracy of measurement numbers, and then figure out the greatest possible error of our measurement numbers. All right, first we need to talk about units of measure. So a measurement number normally has a unit that is associated with it, and we call those units of measure. For example, 20 is just a number, but when we put feet behind it, it's a length. When we put pounds behind it, it's a weight, or it could be a force. And when we put seconds behind it, of course, it's a time interval. So units of measure matter because it gives context to these arbitrary numbers. An example would be a piece of pipe is measured to be 8 feet in length. It is 8 times the standard 1 foot length. So here is showing us that the units is feet. That's all we're dealing with. Don't make it harder than it is. Every measuring instrument and every person making measurements has its limitations. There's always errors with any kind of measurement tool. So we need to understand where those errors can come from. We need to understand how accurate our measurements are. And it really comes down to the tools that we use, but also when we're describing measurements, we need to be able to kind of understand how accurate each of those measurements are being portrayed as a number. And that comes from the idea of significant digits. Now, the precise definition of a significant digit is it's a number that represents an actual measurement. And to determine the number of significant digits in any kind of measurement number that you're given, there's a few simple rules. First and foremost, any digits other than zeros are always considered significant. Pretty straightforward. A zero, however, can be significant if it has one of these 3 attributes. It either appears between 2 significant digits, and we already know that that's just any non-zero number, but it could also be between 2 significant zeros, by the way. So just between any 2 significant digits, is at the right end of a decimal number. So meaning if you have a number with a decimal point in it, and you have what you can think of as a trailing zero, a zero at the very, very end of that number, that becomes significant. So for instance, 3.50, even though that's equivalent to 3.5, which makes you think that the zero is insignificant, what this zero tells us is that we've actually measured whatever we're measuring to a higher degree of accuracy than just the tens place. We've gone all the way out to the hundreds place, and it's a zero because either it was exactly that distance or we rounded, right? So it gives us a level of significance. And it is marked as significant with an overbar. And an overbar is things like, 1.3 repeating. So an overbar on zeros, right? 1.30 repeating. That kind of thing. However, a zero is not considered significant when it's at the right end of a whole number. So if it's at the right end of a decimal, it's significant. But if this number was just 350, that's not significant. And then finally is at the left end of a number. Any number. Kind of makes no sense, right? I mean, why would you have 035? What the heck is that? It's 35, right? Just get rid of it. So those are the basic rules for when something is considered significant or not. Some examples. Okay, you've got a tachometer, which tells you revolutions of an engine or a motor. And it reads 84.2 RPM, revolutions per minute. It has 3 significant digits, right? Because none of them are zeros. And so that's rule number 1. That's easy. The second one, we can see the number 3206 has 4 significant digits because all the non-zero ones are significant, and then the 0 is significant because it's in between 2 significant, so 4 significant digits. Okay. 240 has 2 significant digits because the trailing 0 on a whole number doesn't tell us anything. How about this one? 240 with the bar over it, now it has 3 significant digits. So it's pretty simple, to just apply the rules. It's going to take a little bit to understand why the rules are what they are. A couple more examples, right? 24.0 again has 3 significant digits because the rule for the zeros is if it's after the decimal point, it's significant. So similarly, 0.025 has only 2 significant digits because the 0 is not at the end of that decimal, right? So when you have a decimal number, the 0 has to be trailing, i.e. at the far right-hand edge. So 2 digits on this one, 3 on the one above. Okay, this all comes back to precision and accuracy, the idea of how precise the measurement is and how accurate the number actually, represents that thing. So precision is a measurement number. The precision of a measurement number is indicated by the place value of its rightmost significant digit. So that basically tells you how precisely something was measured. Was it measured just to a whole? Was it measured down to a tenth? Was it measured down to a hundredth, a thousandth, and so on and so forth? The accuracy of a measurement number refers to the number of significant digits it contains. So the precision is the rightmost significant digit. And remember, as we go to the right, it gets smaller and smaller and smaller. So it's basically saying what's the smallest level of accuracy, right? That's how precise it is. And then accuracy is just the total number of significant digits. So it's accurate to 3 significant digits. It's accurate to 5 significant digits. But it's precise to the 10,000th place, or it's precise to the 100th place. Okay, so let's state the precision and accuracy for each of the following. If you want to pause the video and kind of check yourself and then hear what I have to say, you can always try that. So 4.01. First and foremost for A, how many significant digits do we have? Well, we've got 2 non-zeros, so we know we have at least 2. We have a 0, but it's sandwiched in between 2 significants, so we have 3 significant digits for that first one. So we already know what the accuracy is, right? The accuracy would be 3 significant digits. The precision is the farthest to the right accuracy, or the farthest to the right, significant digit, which in this case is the 1. Which is in the hundredths place. So it's precise to the nearest hundredth, and it's accurate to 3 significant digits. Okay, 40 seconds, right? The 0 is not significant. Therefore, this number is only accurate to the nearest 10 seconds. And so it's precise, to the nearest 10 seconds. And it's accurate to only 1 significant digit. This one, we've got 4 significant digits. It's precise all the way down here to the nearest tenth of a second, and it's accurate to 4 significant digits. So again, application, pretty easy. Understanding why can be a little tricky. Okay, the greatest possible error of a measurement is defined as half of the precision of that measurement. So if you're reading the measurement yourself with some sort of tool, the greatest possible error is half of the smallest division on a scale of the measuring tool. The idea is pretty simple. If you think about, we've all dealt with rulers, right? And so, let's see if I can move this. There we go. Can I rotate it? No, maybe not. Let's say you're measuring something, right? And it starts here. And it goes down to like right there. And it ends in between these 2 lines. Well, you can't tell precisely if, the length is on this line or the other line, so you know that your greatest possible error is half of that total distance, because you're either going to round down to here and call it that, you're going to round up to there and call it that. Well, the worst that's going to happen, right, is you're off by a half because you're rounding. So that's the idea of where that comes from. Okay. Suppose the weight of a steel bar is given as 14.6 pounds. The weight of the bar has been measured to the nearest tenth, right, of a pound. So that's the precision. The greatest possible error is half of that precision. So it's accurate to within 0.05 of a pound, or 5/100ths of a pound. And again, that comes back to rounding. Right? Think about all of the numbers that would round to 0.1. So you could have 0.05, right? 0.06. These would all round up to 0.1. And then ... 0.11, right? 0.12, all the way down to 0.14. Because if it went to 1.5, it would round up to 0.2, right? And if it was smaller than 0.05, like 0.04, would round down to 0.0. So in this case, you can see that the biggest difference, right? So here's the largest and here's the smallest. The largest difference between the two, with our guess of being, or not our guess, but our rounding of 0.1 is this is off by 0.05, this is off by 0.04. And technically you could think that you can go to 0.14999, right? Repeating, which is really very close to 0.15, which is off by that 0.05. So that's the idea. That's where this error comes from. It's just always half of the next level of precision, because that's how we round, right? 1/2 of that next level tells us whether we go up or go down. So then if you want to be completely precise of measuring something, you would say it's 14.6 plus or minus 0.05, because we know that that's kind of our margin of error, so to speak. Now, a tachometer reads at 4,700. So the precision of this measurement is 100, because remember the two zeros are insignificant, right? So the smallest significant digit is the hundredths place. So its precision is to 100ths, because it looks like it's been rounded to the nearest hundred, right? So the greatest possible error is half of that, or 50. And yes, you can just take 100 and divide by 2, but you can also think of, the next spot here and put a 5 there, and that's why it's 50. So either way you want to think about it. So really this is telling us that the RPMs are somewhere between 4,750 and 4,650, because those would all round to 4,700. Now, obviously, 4,750 would round up to 4,800. It's the idea that it's 47.499999. It's 4,750 with just a smidge less. Okay, another example. Suppose you're measuring the lengths of two pieces of tubing with a ruler, as shown above. You can see how one is just slightly over that little hash mark, and one is just slightly under that hash mark. And that first hash mark, right? How many of them are there? You'd have to count them up. We got 1, 2, 3, 4, 5, 6, 7, 8. So that's an eighth. It's an eighth of an inch. So this one's a little bit bigger than an eighth of an inch. That's one a little bit smaller than an eighth of an inch. So because we don't have any smaller marks on the ruler, the smallest division being an eighth of an inch means that's as precise as our ruler can measure. So our measurement is, precision is to an eighth of an inch. So whatever we measure is going to be accurate to within 1/2 of that. So it's going to be accurate to within 1/16 of an inch. And that's what we're talking about with this slide. Tolerance. Well, Oftentimes, technical measurements and numbers shown in drawings and specifications have a tolerance attached to it so you can understand what the precision level is. So for instance, a dimension on a machine tool might be given as 2.835 plus or minus 0.004 inches. This means that the dimension should be 2.835 inches to within 4,000 of an inch. So basically it means that the measurement can be off by a little, but it shouldn't be off by any more than 4 thousandths of an inch. And if you kind of add and subtract that, what that means is it wouldn't be any bigger than 2.839 and it wouldn't be any smaller than 2.831. That's tolerance. It's the tolerance just gives you your margin of error. If you've ever done any statistics, it's that plus and minus thing. So that's always considered kind of a margin of error. And when we're talking about measurements, it's just given a different name and it's called tolerance. Okay, we'll stop here and our next video will pick up right where we left off with addition and subtraction of measurement numbers.